All right, I welcome you to the part 3 for the intro to the organic synthesis, the multi-step synthesis. First, I want to show you this little piece of molecule that's heavily used in the biosynthesis in plant and animals. If you have a double bond there, it will be terpene. 5 carbon unit. You know, I use this a lot in my examples. So in the biosynthesis, these 4 carbon unit of terpene will be used to build small natural molecule like this, or the bigger molecule like a cholesterol. Can you find the terpene here? If you can, how many can you find? Take a moment and try. There. You see, you have 2 units. This iso group here for 3 carbons, and then 2 carbons, this tail right there. Also in this unit, you have 2 methyl and 3 carbons iso propyl unit, and then 2 carbon tails here, right there. So 2 terpene units are bound together in a certain way, and life forms generating this unit. And see, you can find some more terpenes in this cholesterol. Well, actually, this is not the original molecule. There is a precursor before they remove some of the methyl groups. You know, they had methyl group here, 2 methyl groups there in the precursor form. So we cannot find all the terpene that made up this, but we can still find some after losing methyl groups, as you can see here, right? And then you can see 1, 2, 3, 4, 5. You can see 1, 2, 3, 4, 5 here as well. You can build all of these using terpene, as you can see, right? So, you know, in organic multisynthesis, it is important to see where the some pieces that you use in the product. It's tricky and it needs practice. Also, your synthesis task could be making something like this exotic molecule. This is actually real anti-cancer drug called Taxol. And you can see there are 4 rings, and one of the ring is really big. And putting all together takes a lot of effort. And at the same time, as you can see, certain carbon has a specific stereochemistry. So you need to also selectively form that stereoisomers. And this takes weeks, sometimes a month of, a couple of months when professional synthetic organic chemists work on this compound. So these are probably the ultimate goals of the organic synthesis. But for us, we just need to learn some foundation for it. So let's get back to the foundation. So instead of those heavy molecules given to you, imagine you got this kind of task. And try to figure out in this multi-step synthesis rather consider simple one. What type of skill you need? And I pointed out few of them already in the previous videos. Some step, as you can see, you have a reactant and the reagent and condition, so you need to apply regular mechanistic knowledge to figure this question mark. And also here you have this double bond given and the HBr and the peroxide. As you can see, this is an anti-Markovnikov addition of HBr, and Br goes here, right? After removing double bond, that's your question mark. Then once you figure this out, then it's the same type of problems. You know what this is, so you have the reagents and conditions. So by applying the typical mechanism, you can figure out this question. So you had question marks in series, but if you tackle one at a time, it just becomes typical mechanism steps here. But what about there? Yeah, you can figure out this question mark, but there are many question marks, then you got that. So this you cannot go forward. So that's when you need retrosynthesis. You can try a few things, but whatever fits into this two-step, you can propose as an answer. So take a few minutes and try to figure this out. Alright, so here we figured anti-Markovnikov addition. Then you have a weak base water and the heating going on. There's a tertiary, secondary carbon with a leaving group. So you can lose the leaving group and the carbocation shift to the tertiary and become positive. With the same method, there's no racemization, so just attack and get the water here with the H2 and positive, but one of the hydrogen will be taken by water molecule, so you end up getting this final product. So whole series of the reaction is to get this one from here. Obviously, this is not most effective method to make this. It's just a barely practice of multi-step synthesis, connecting elementary simple reactions together. How do you tackle here? Well, in order to form double bond, you are already, having leaving group, so you can simply do E2 reaction, but they ask you to make something else that can give you that from this. And I hope you remember that we have other type of leaving group, but I like to pick OH. You can propose this. If I have this, then I can form this using H2SO4 with the heat, dehydration reaction. Then I can form this by doing SN1 like we did here, H2O with the heat. Then certainly you complete it. Well, you can put other things here and try same thing, but I'm not gonna spend time on that. So this example is giving you simple cases, rather, where you just have a mechanism skill and then a simple retrosynthetic analysis allow you to fill up all the question marks. I hope this exercise is bringing some memories back so we can move forward from here. So in your toolbox of organic synthesis, what do you have? What skills I mentioned? I mentioned that you need to know simple reactions. Of course, including mechanism, it always helps because you have to run mechanism sometimes and the simple memorization sometimes don't work. Also, you need to know what reagent is used for a certain transformation, because you don't always get reactant and the reagent. So you get situation where you have reactant and product, then you need to come up with what reagent is allowing that assumed reaction. If you cannot find anything, then you have to choose other assumed intermediate precursor. That for that reason, you need to know your simple reaction well, including these. So what do I mean by simple reactions? You know all of those SN1, SN2, and E1, E2 rearrangement and addition reaction, etc. But also new reactions like this Williamson ethers reaction, or some famous Grignard reaction, etc. You need to know all those simple reactions, memorized and understood. Not only that, when you remember the reaction last time in the video, I asked you to know those reactions with selectivity and reactivity associated with each reaction. And by saying that, I meant like whether the addition, say addition reaction was anti-addition or syn addition is included, or when you do when you think about, you know, anti and syn was the stereo, right, in the space, but in the connectivity perspective, addition also can be divided into Markovnikov or anti-Markovnikov, those things. Or when you do elimination, whether the reaction will be Zaitsev or Hoffman. What else? Well, when you do substitution, you could have inversion of configuration from R to S, S to R. Or in SN1, you could have a racemization. So when you notice the product is a racemization product, then you have to connect with the SN1. That gives you idea about what reagent you need, things like that. Then, in the previous video, sometimes you need to think backward, as we saw here, and come up with some proposed precursors through retrosynthesis. In the future, soon, we should be doing protecting group. Since the realistic molecules, such as amino acid, having multiple functional group, right? Amino group, carboxylic acid group, and the side chain could have other functional group as well. So those functional group interfere reactions on other functional group, so you need to sometimes protect them. Along with that, you will have cases where you need to activate some functional group that is not reactive enough. So activation group. Those should be in your toolbox. So whenever you study a certain simple reaction, you have to learn in these manners. Then, in the analysis, right? Whether you look at the final product and try to do retrosynthesis, or you try to compare reactant and the product to analyze the differences. When you analyze, you have to do in two aspects. So two aspects you should have in your analysis is, first, you have to notice what functional group transformation you have. such as alkene gave you bromine, but in anti-mark. Bromine compound, bromo compound gave you alcohol, and after rearrangement, that kind of thing. You need to notice the functional group transformation. And we haven't spent much time on this, but the second one becomes more important in real multi-step organic synthesis from now on. That is carbon skeleton. You need to know where is your carbon, and then how many carbons are chopped off, such as in ozonolysis, or how many carbons being added. So you need to start caring about carbon. When you add the carbon, you still need to know whether the carbons are added in conservation of the stereochemistry or the inversion, or whatever the associated aspect of the chemistry that we discussed over here. So those are the two aspects of analysis in organic synthesis. Okay, let's look at this. What do you see here? I have reactant and the product shown, yes, and the functional group has been changed, but you cannot connect directly. It's not SN1 only because you have a rearrangement. I've shown you this many times. You cannot rearrange from the tertiary to the secondary, so you know already from the experience. You need to do elimination and do anti-Markovnikov addition. However, with even that idea, you don't get CO double bond in anti-Mark, right? In anti-Mark addition, you have only option 2. You can add halogen, especially bromine, and you can add oxygen, OH form. So you can see, you must analyze by comparing it, but also on each discovery you have to associate with the other simple reactions. So as you said, if you do retrosynthesis, I gain this, by disconnecting there. I know, I gain the oxygen, but you cannot gain double bond, so you can think of it. What do I need to form this? And there could be many options, but for you guys, you only have a couple options, right? One of the best is if you have this, you can oxidize it. So in the oxidation of primary alcohol, you can get ketone. So, this is useful. Then I can actually react. This is a reaction arrow. This is a retrosynthesis arrow. So with the reaction arrow, this is the reactant. That's the product, right? So what do you need for synthesis? The conversion of functional group from OH to the ketone. Well, you need the oxidation reagent. Let's just say you can use chromic acid, H2Cr2O4 with the heating. You can memorize this. Then you say, how do I get this from there? I have a rearrangement. But we've seen this before many times. And I mentioned earlier, if I have this double bond here, then I can do anti-Mark addition of OH, one of the two anti-Mark addition. First step, BH3, THF. Step 2, peroxide with the hydroxide. Then we all know how to get here, right? But we don't want to use a too big strong base for elimination because the substrate is a tertiary. So I'm gonna go safe way, just 1 or 2 carbon. So you get the E2 to form this. if you have to provide answer in one box here, then you will have to use a numbering, right? 1 ethoxide, 2 this BH3 THF, 3 peroxide with hydroxide, 4 chromic acid with the heat. Then this would be correct answer for this transformation. So this example illustrates like you need to know these simple reactions of E2 and antimark addition of OH and oxidation. But you cannot just simply put them all together, right? You need to think about the logical reasoning why we had to think about this by assuming something in retrosynthetic approach. And when you add this, you should know it's on the less substituted carbon in comparison to the reactant. You are assuming this is done from this alkene, not other type of alkene. This type of thinking is not part of the, memorizing simple reaction. You need to know simple reaction with a lot of details that I illustrated earlier attached to it. So let's try another example. This example also, you have reactant and the product. And then you can see it's not simple functional group transformation. Right? It's not just simple functional group transformation. You added more carbons over here. So how do we do it? Well, since we don't have anything that can make this conversion in one step, you can go both ways, whichever is more easier for you. You can try from here something and then continue, or you can get some help by thinking backward retrosynthetically. So what I noticed is like you need to find out the carbon skeleton, original one, where it is. That thing is right here. Right? Isobutene. Though it lost double bond, we don't really we are not really scared of losing double bond. We can add something and remove double bond just like that. But also I noticed presence of oxygen here. That gives me a couple ideas. But you can connect this to this reactant, right? This. It's awfully similar. If you have this retrosynthetically, you can say, I can make this because oxygen attack on this carbon and you need this carbon groups. And attack on this one, you have to lose something to have oxygen, replacing it. So replacing something and that group is lost, that's the leaving group. So you can put chlorine there. If you don't like the fact that this is a weak base and maybe it will have a hard time to attack, you can try a couple catalysts, okay? You can first try H+. H+ can get on the oxygen, making it a more reactive, inducing more plus charge, giving more chance to attack on the carbon. So this even weak guy can attack and then kick this out eventually. Or some of you remember that you can actually convert this to more stronger base like this. How did you do it? That's when you need to know the simple reactions and remember the reagents. So what reagent you need to do this? This is the moment you need to remember that. So if you don't Just think about the principle. This is quite unstable base. How do I make this? By removing hydrogen. Well, the hydrogen's are acid, so you need the base. The base has to be more unstable than the product. Therefore, you need something like H minus, right? Or remember, we can just use a sodium metal, lithium metal in radical mechanism. You can remove the hydrogen as well. So please remember those. Okay, so now this can happily attack here and knock this out, and you can form that. I'm not here trying to show the full mechanism, okay? I want to focus on the synthetic idea so you can follow me easily. Then how do you get this from there? Well, you can see addition reaction, and especially anti-Markovnikov addition. So you can do, you can do that in 2 steps. We just did earlier. pH3 in THF ether solvent, then peroxide with the hydroxide, and don't forget numbers. Then you got it. Well, some may say, I can do it different way. I told you in the beginning, you can do it in different way. You can put anti-mark way the bromine on this carbon and simply do SN2 using this stronger form of acetate, benzoate, as a nucleophile, and you can do that as well. So no problem. How about this? You may want to pause this video and think about it. This looks simple, right? You are replacing chlorine with the OH. Simple transformation of functional group, you may think. So you will start to remember some simple reactions you can do. And that's when you make a mistake if you are leaving out the details about like, stereochemistry, inversion or racemization, these things. You have to pay attention to the stereochemistry. This is wedged, and that's still wedged. If you want to do substitution in SN2, then it should be inverted, but it's not. If you want to do SN1 then, right? SN1 have a half of the retention of configuration. But if you try that, you know the secondary carbocation eventually move to the tertiary, so it doesn't work. Then you are saying, okay, I can do elimination. Then I can do elimination with a, forming double bond there. Then you do anti-Markovnikov addition of OH with a borohydride, and perfect. But do you really think the OH will be coming up when the isopropyl is sticking up? The pH3 will approaching from the opposite side of this. So the OH will be going away, not coming towards you. So that's not going to work. So what would you do? Then you think about it. If I get this from some other functional group, not SN2, addition, E1, whatever, what other reaction you know? So if you can get this functional group, right? Then you can make this. When you try to put H minus with some reagent attacking here to make the OH minus, then oxygen minus will pick up the H plus when we quench the reaction. When you do that, this reagent is not approaching from the top because that's the surface protected by the bulky group. So the steric issue make the kinetics slower for making the hydrogen coming from the top. So this will obviously coming from the bottom and shooting up to this carbon and pushing the oxygen single bond upward. So it goes this way, then you can quench. So there are many reagents but you can use such as lithium aluminum hydride, the ionic H minus. Then after forming oxygen minus, you can put H plus to quench. Then you say, how do I get this? We did this before in this video. You cannot simply put a double bond replacing chlorine. You gotta have, again, retrosynthetically, you gotta have OH. Then I say, does it matter whether the OH is up or down? It doesn't, right? Because if you oxidize it, sp3, the one that could have stereochemistry, will lose one hydrogen and become sp2 carbon, which is a flat. So there is no RS anymore, so it wouldn't matter whether this is R or S or wedge or dash. So it doesn't matter. It all depends on what reaction you choose from here to there. So that's another thing you should be careful. You see, a lot of thinking you need in the multi-step synthesis. So when chlorine is being replaced, do you want SN1 or SN2? And you all know, we've talked about it many times, chlorine in SN1, if you remove, carbocation will shift. So it must be SN2. SN2 need this base in strong form. Not weak form water, but strong form of hydroxide. If you do it, the attack on this carbon must coming from opposite to this. So the hydrogen was here. It's coming from the bottom and kick this out, but pushing hydrogen up, and the OH will stay down. So this is the case. Then you go from here to there. I'm using regular reaction arrow. You can do oxidation. You know, we talked about chromic acid. Then from here to there, I showed you already. And you can summarize these things here, and you're done. Not too bad, right? Okay, in a couple minutes, I have to finish this. Due to the equipment problem, I cannot do more than 30-something minutes. So, what do you see? You need more thinking here. See, you need to find these pieces here and determine where you want to disconnect. You have a benzene and the 2 more carbon. You find the benzene and 1, 2 carbons. Or you find the benzene, 1, 2 carbons. This carbon is counted twice, so maybe I didn't count correctly. So let me do it again. pH, benzene 1, 2. So I may disconnect here. Then I find pH 1 and the 2. Oh, I need 2 of these guys. That you should catch. That's possible when you analyze them, not only functional group, right? Also carbon skeleton. So please remember this. This is very important. Just like the thermodynamic control or kinetic control, you always care about both. So in the synthesis, you care about 2 aspects of analysis. So after cutting, you know, you have this piece with the OCH3 and this piece. Then which side you want to put negative and the positive, right? But you notice there's oxygen, so naturally this carbon is a partially positive. So I would normally try the natural flow. So this is a positive side, that is a negative side. Then you are saying, how do I make this negative side of carbon there from there? So let's try. How do I make this? Well, how do I make a carbon negative? You guys all know. This is from, you know, if you have pH with chlorine or bromine there, then you can simply put metals there. Then you can have some type of a radical reaction. Then you can create, corresponding to this, you create pH with the Mg. I need to be careful. Making 2 carbons, so one more carbon, one more bond there, MgCl, right? So 2 carbons are there. I'm sorry for the rush, 2 carbons there. Then this carbon staying as a partially negative and nucleophilic, so you made it. What about this part? Well, you cannot have OCH3 right away from there. But if you go backward, right, retrosynthetically, if you had pH with the O minus, then you can make this with the CH3Cl, Williamson ether synthesis. You can attack and kick out, you can make this. And how do you make this? Well, O minus, you can make it retrosynthetically. You see, you need a lot of retrosynthesis. If you have double bond, then you can add H minus. Without quenching, you can have oxygen minus. Then how do I get the oxygen double bond? We did that, right? So this is not anti-mark. You can put OH right here. pH and the OH. Just a regular reaction of H3O plus. So we eventually created 2 paths. Yeah, so what's missing is this. When do I connect this negative to this molecule? So look at this. I need to add this negative here. When is the best time? There, right? So here you connect this molecule with this molecule together. What happens? The carbon negative attacks here. So let me put it in different color. I'm really running out of time, okay? If I forced to be stopped, please excuse me. Maybe in another video I'll try to come back, but we'll see. This attacks here and breaks, and you get the negative just like that. And you still have a pH, you still have a CH3, but now this guy is attached here, okay? Attached there, CH2, CH2, pH. Then there, which is this guy, react with a CH3Cl, and then you attack, and you get this one. So this is your product. I know this particular example is a little advanced one for you as of now, but it will get better. So I just wanted to show you what is the ultimate goal, and we'll have time to go over some of the reactions I showed you here in more detail, so don't feel too bad. And hopefully this helps, and I'll see you in other videos soon. Thank you.